Speaker today is Gregory Pearlstein from Texas A&M University, and he's going to talk about infinitesimal Torelli and rigidity results for a remarkable class of elliptic surfaces. Thank you, Gregor. Go on, please.
Okay. So, all right. So as usual, okay, first off, it's a pleasure to be there virtually. I just wasn't sure if I could make it in person. Okay, so I'll be talking about some joint work with Chris Peters. So as usual, the trade-off here is that if you get the biggest possible font, they don't get to see the whole slide at once and have to move around, so that's a bit jarring. Okay, so we're going to prove some rigidity and some Torelli theorems for a certain class of elliptic surfaces, and maybe I'll spend some time to talk about the motivation of these results. So the first motivation or old results of the faultings in Peters. Okay, so we start off with a smooth projected curve S bar and some finite set of points on S bar such that the complement only has an automorphism, and we let MG denote the moduli space of smooth projected curves of genus G. And we assume that G is bigger than 1. So then Erkelov proved in 1971 that if we had a non-constant map mu from S to mg, then that is rigid, keeping both like the source, which is the curve S, and the target, like mg, fixed. Okay, so now there's an obvious question you can ask about this is because, well, I mean, a curve is very close to being its Jacobian, so you could replace curves by Jacobians, and the same result holds after you replace mg by the moduli space of abelian varieties, ag. And so faulting, well, the space of infinitesimation of a period map from S to ag, that's canonically identified with the direct summand of the monodrome invariant endomorphisms, which are pure of Hodge type -1, 1, and so consequently, if f is non-constant, f is rigid only if this group of endomorphisms is pure of Hodge type 0, 0. So if you have a pure structure of A, then its endomorphism is a Hodge structure of weight 0, because the dual has weight minus k, but you all know that. Okay, so then Chris Peters thought about, well, what would happen if we just thought about period maps and not about varieties or curves, and so he proved the an analogous result for maps, for period maps. Now here we should say one of the main tools that gets used with this, because I don't think I'm going to have any time to talk about the proofs, because I didn't have time to talk about it when I gave this talk a week ago. This depends on some very subtle kind of calculations of bisectional holomorphic curvature. So that's the means that will go into the proofs of the theorems that I'm going to talk about today. So now motivation are certain mixed Torelli theorems. So on the one hand, another thing that we know is that for curves, we have these Torelli theorems, same things for abelian varieties, K3 surfaces, hypersurfaces of sufficiently high degree in projective space or weighted projective space. Okay, so a long time ago, you can see the year is 1977. Of course, the question was a bit earlier than that. Griffiths had asked if the P map could have like positive dimensional fibers in some geometric example, and so Kunev gave a geometric example of a family of connected surfaces with H20 is 1, H11, not primitive, just H11, is 19, for which the P map had positive dimensional And so maybe it's important to say this, right? That I mean, this is of the same flavor of the period domain of K3 surface. Okay, so this is not something about that the Griffiths infinitesimal period relation fails, because the Griffiths infinitesimal period relation is always so. Geometrically, here's another typo. The example derived from a Galois Z2 cross Z cover of the plane branched along two cubic curves intersecting trans. So, one of those, well, that's x0, two cubics, F and G. So then you can create a surface in P1, 2, 2, 3, 3. So what do you do? So it's supposed to be branched along the line. So you take F and you put x0, which defines the line. You square it. Then you have y1 and y2 in degree 2. And then to make everything work, you take two variables in degree 3. Okay. So one thing I should notice about these surfaces is that it has a unique smooth canonical curve of genus 2. So in 94, Letizia proved that basically if I had two generic Kunev surfaces, notice the change from one spelling to the next, and y and y prime were their canonical divisors, then if the polarized, so here polarized means graded polarized, mixed structures of the complements are isomorphic, then x and x prime are isomorphic. All right, and then so another like example that I'll discuss is some old work of Hain and Bulta, which said that if I had, okay, so what do we know? So of course we have Torelli for smooth projective curves. We could think about smooth to some kind of mixed Torelli for curves if I remove a bunch of points, but if I remove only 1 point and I try and look at the Hodge structure on H2 of a smooth projective curve minus 1 point, then I just won't see that point. But maybe one of Hain's ideas was that this mixed Hodge structure in the fundamental group is a bit finer, so there is a nice pointed Torelli theorem that says that x and y are smooth projective curves, and P is a point in x and Q is a point in y, then with the possible exception of 2 points on x, whenever you have a ring homomorphism which preserves these mixed Hodge structures, then there's a homomorphism of these things as pointed curves. And Sui and others use more examples of this kind, but I think I've given a rough overview. And part 2. Okay. When does one have like rigidity for mixed period maps? And so this is joint work with Chris Peters. So the basic idea is we'll take x as smooth projective dimension d plus 1 and y as smooth divisor. Then we can look at the complement, and if we look at the primitive part of x in degree d plus 1, then of course that's pure. Then we get the comotion of the complement, degree d plus 1, and then we have a kind of residue map down to the homology of y twisted by minus 1. So, so basically, this picture here is just for a curve which would have h10 or 1, and then these classes of type 1, 1 you can think of being like the dz over z's. Okay, so our Cattani result for hd plus 1 of u is rigid in the minus 1, 0 directions if the following two conditions hold simultaneously. First, the monodromy representation of the pure part in weight d plus 1, that has to be irreducible. And the next thing that we need is that the dimension of this pure part is strictly bigger than the dimension of the cohomology of degree y. So if addition period are rigid, then the period map is just rigid in all the horizontal directions. And so for some applications of that, we could look at families of quasi-projective curves of genus G with less than 2G punctures. And another application, those Kunev surfaces I talked about before on the previous page were generalized by Andrei Todorov. So these are called Cattani Kunev Todorov surfaces. All have a unique curve, and so the result is that this family, or the variation mixed structure that comes from taking the Todorov surface and removing its unique canonical divisor, rigid, if all the following is true, the family of curves is rigid, the essential part of the transcendental part of the K3 variation is non-constant and rigid, and the mixed period map is an immersion. And so let's not worry about modular here. Anyway, but the natural 12-dimensional family, and that family is modular, and this rigidity result holds as soon as you have a sufficiently general generic subfamily of that kind of natural geometric family. So any questions so far? Questions too trivial? Pick up the pace? I don't know if there are many students here trying to learn things. Questions?
I think no.
Once, twice. No?
Maybe your microphone is, I think it's a little bit problematic. Are you touching it, or sometimes the voice is not? It's okay.
Let's see. Is this better? Worse?
Yeah, let's go on. And
Better
see.
or worse?
Okay.
Oh, okay. Okay, I can try and use some headphones. I don't know if that will help or not.
Okay. So então agora. Greg, our specialist told us that maybe your internet is not so strong. For
Better or
example,
worse?
if you turn off the video, it might get better. I mean, the video, your picture.
I thought you would turn off the video.
Yeah. Okay.
I don't know. Better?
Okay,
Hear
let's
me?
go on and let's see if it's better or not.
Is it better or worse?
So if it is not, it's still, your video is still there.
Okay. All right.
No, just turn it off. I didn't, we just see
My
the
video
slides
is
and your voice. Yeah, okay, now it's better.
okay. Better? Okay. All right. Back to the talk. Okay, so. Okay, and now more recently, I'll talk about a third motivation. So this was joint work with Patricia Geraldo, Lucas Schaffler, and Deng. So here we were considering generations of a class of Horikawa surfaces, which are given by degree 10 hypersurfaces in P1125 to hypersurfaces of the form. Okay, so let me, because I didn't put in the degrees here. So W is degree 5, X is degree 1, Y is degree 1, and Z is degree 2. Okay, so this A plus B plus 2C is just the standard condition homogeneous degree 10. And now this other condition here is the condition in this particular case that when you degenerate to 0, you actually a unimodal singularity of type E13 in Arnold's list. Okay, so this is just a bunch of high school algebra, so I might ask what happens. So the main point here is that after we multiply this defined equation squared, we can rewrite our equation as wz squared is the same coefficients, but that's x, z to the a, y to the b, and z plus 2c minus a. Okay, so that means that our surface is now birational to a degree 14 hypersurface p127, okay? So originally w had degree 5, so multiplying it by z makes it a variable in degree 7. Had degree 1, z had degree 2, multiply it together, that's a variable degree 3. Y just stays degree 1, it just stays degree 2. We can ask in this weighted projective space, singular locus, it's just the points 0, 1, 0, 0, 0, 1, 0, 0, 0. Okay, so and okay, now a generic degree 14 hypersurface in P123 we'll have, okay, so now what happened? Y stayed Y, Z stayed Z, X became T, and S became WZ. So if it's generic equation, then of course I'm going to have S squared, and I'm going to have Z squared with none coefficients. So that rules out it passing through these 2 points. On the other hand, there's no way to avoid passing through this singular point of P1237. So on the other hand, generically, we will have t to the 4th z. So if I take the gradient of this, it'll be non-zero. So what does that mean? So that means generically, this surface is smooth except for a kind of ambient singularity coming from the weighted. So this is going to be quasi-smooth. Okay. And so, well, that's what I would get in general. But now these E13 surfaces, these ones that are done by this original set of conditions here, 15, okay, they never in Y14, Y plus Z, or Y10T. So that means the gradient is always 0 at this point 1, 0, 0, 0. So they always have an A1 singularity. So the general surface, degree 14 hypersurface in this weighted projective space, only is quasi-smooth. It only has singularities coming to the ambient space. The particular E13 ones I wrote down, they would actually always have also an A1 singularity at a smooth point of that weighted projective space. Oh. So now, in light of what I just said, Chris Peters and I, this is kind of a bit of reverse engineering, we wanted to think about all of the quasi-smooth surfaces in P1 to AB of degree D is 4 plus A plus B, where A and B are coprime, such that they have amplitude 1. So that condition will automatically imply that the geometric genus of all of these surfaces is 1. And so the next thing is what can occur. Okay, so I'm not the proof of this proposition because this quasi-smooth condition is a purely combinatorial thing. Maybe I should say that, okay. If you're not used to working with weighted projective spaces. If your weighted projective space has a Fermat hypersurface of degree D, then the generic hypersurface of degree D in that weighted projective space quasi-smooth. So in many cases, in situations where you have one of these Fermat gadgets. So in that case, like, you don't have to do any combinatorics. If that doesn't happen, then it's kind of rather delicate whether the surface has this or not. Okay, but anyway, at the end of the day, it is a combinatorial condition. You can sit down under these hypotheses, there's 1, 2, A, B, and the degree is this, and grind out what could happen. So it could be degree 14 in 1, 2, 3, 7, but I mean, I kind of set up the problem to be that way. What's kind of very interesting is actually there's only 4 cases that can arise. So maybe I say, okay, so x0 is going to be degree 1 always, x1 is going to be degree 2 always, x2 is degree A, and x3 is degree B. Okay, so now what can we say about like the list that appears? So the example A and B give properly elliptic surfaces, not K3 surfaces. Okay, these direct dimension 1. Whereas cases C and D give K3 surfaces. Now they all have 1. Okay, so now C3.1 is all I copied from. Okay, which is on. Okay, so which has that title, remarkable class of surfaces. Okay, so case C and D, maybe they're not so exciting because they happen to be birational to this famous list. There are 2 entries in this famous list of 95 K3 surfaces produced by Reed. Okay, so then that's more for people who are already familiar with that work. Okay, so what's our next step? So our next step is we want to construct moduli spaces for these spaces. Now, another thing which is maybe not clear, I haven't worked on this before. So the standard GIT theory is developed for like reductive groups. Okay. Now, it turns out that in one of these weighted projectives, then usually the automorphism group of that weighted projective space isn't reductive. Now, there has been a lot of work on non-reductive GIT theory, but we're not going to use that. So what we're going to, maybe I should explain why it's not reductive, okay? So let's take an example, maybe this one here. Okay. So x3 has degree 7. Okay, so when you go to write out the automorphisms of this weighted projective space, the transformation for x3, well, x3 can go to a non-zero multiple of x3, plus then you have to figure out all the ways you can add up to 7 with these other. You can have x3 to, I don't know, 0 x3 plus a1 x0 to the 7 plus, I don't know, a2 x0 5 x1 etc etc. So that part, which is not which is low, adding on the multiple of x to the 7 and x to the 5, sorry, x0 to the 7, x0 to the 5, x1, that all is giving you something which is unipotent, right? So that's not going to give you a reductive group. So, as I said, there's a non-reductive GIT theory. We're going to do something which is a bit simpler, which is more like what you do with manipulating equations. If I give you just an ordinary equation in degree, then one of the things that you learn very early is that you can make a change of variables to keep the x cubed term but eliminate the x squared term. So that's what we do. So what we do is we say, okay, there's this big non-reductive part of this automorphism group. So what we're going to do is just make some transformations which are going to kind of absorb all of this non-reductive part to get some normal form, and so what's left over will be a reductive group. So, okay, that's the next part of this theorem, so that you do this trick that I just said, and you the automorphisms preserve this normal form consists of transformations which are just xj goes to cjxj for some element cj and c star. That's certainly going to give you something reductive. And then there's a few more conditions on the weights which are not, I'm not going to reproduce them here, but okay, so you get a reductive group to take the quotient, so there is a moduli space. The construction of normal forms, again, this is just like what you do with the cubic. You get rid of the x squared term, that's high school algebra, not to repeat it. Okay. So in each of cases, the points in the Minkowski open subset of this group of things, this set of things in normal form, are quasi-smooth hypersurfaces. They're G-stable, that's the geometric quotient, and it has dimensions 18, 17, 16, and 18, etc. Okay, the proof of that is you just count the number of monomals which appear, and you mod out by the automorphism group. Okay, so maybe I'll just quickly, this the last time I discussed it, so I am going to move it to the end in case somebody, I guess we have time, but I don't think we will. Your next question is, well, how big is the global monitoring group of these surfaces? And the answer is that it's essentially as large as it can possibly be. Okay, but I think I will keep saying. Let me check. This last page is still about one. So, any questions before I start talking about the elliptic fibration structure of these surfaces? Is the audio better now, or
Yes?
does anybody hear me?
Yeah.
I'm talking to the wall. Oh. All right, so you think after all this time I would know how to give a Zoom talk. All right. Okay, so the elliptic fibration structure. So that is surface in P1 to AB, which has singularities at these 2 points, which is the only thing that happened in our case. Minimal resolution of singularity does not necessarily give a minimal surface in case C and D. So you do the minimal resolution, and then you're going to have to do a little bit more to get the minimal model in cases C and D. In cases A and B, there's nothing extra that has to be done. Okay, so now we can use the Griffiths residue calculus for smooth hypersurfaces. I don't know if there are any students present, but okay. So the idea is if you want to calculate the Hodge numbers of a hypersurface in a weighted projective space, an ordinary projective space is you just look at the polynomial ring. In this case, it's C of x0 to x3. You take your defining equation, you mod out by the Jacobian ideal generated by those partial derivatives, and you take the piece in the correct degree. Okay, so this can be, I mean, Carlson wrote some Sage to do this. I mean, you can also do this on your favorite computer algebra program. However you do it, it's easy to calculate what the Hodge numbers of these surfaces are. As I said, PG is 1, so H0 is 1, H11 is this. And now you can also calculate the number of projective moduli. And I mean, that's also just, that's a straightforward calculation that maybe I won't discuss. Okay, so now what we want to do. So now this is about surfaces, so there's no way we're going to avoid Noether's formula in this. So we resolve singularities and see what comes out. So x prime, so what is x prime? X prime was not the minimal resolution. It was the minimal model. Okay. So x prime is always a simply connected surface. I mean, simply connected just becomes, it's a hypersurface of dimension greater than 1 in a weighted projective space. So x prime is a simply connected surface with its Euler characteristic 22. K squared is 0 and B2 is 22. Okay, and it has signature 319. Okay, so let's be maybe clear on this, right? So at first glance, this looks exactly like a K3 surface, right? I mean, you're not seeing anything different than a K3 surface. Okay, even though, as I told you, I mean, in case A, B, the Cattani dimension is 1. Okay, so in case A, the general surface excellent is cyclic singularity at P2. We don't have to worry about the types here, and but you can resolve that with a rational curve of self-intersection -3. Case B, maybe this is not so critical to say, but anyway, one can come and just grind out what all the possible types of singularities of these surfaces are. Does anybody have a question about this?
I think no.
Once, twice. No? Okay.
No.
So now the next thing that we want to do is I said they're elliptic surfaces. Okay. So you have to do some work here, right? So back in the ambient weighted projective P1 to AB, you just have this map x0, x1, x2, x3 goes to x0 squared and x1, and of course that P1 should have the one up there. So that induces an elliptic vibration from the minimal model P1. So there'll be some point where this map is not defined because it only depends on these first two coordinates. But when you go to the minimal model, there is actually a well-defined elliptic vibration. Okay, and so in cases A and B, as promised, this surface has Cattani dimension 1. And in cases C and D, the minimal surface, the A3 surface, of course, it has Cattani dimension 0. Okay, so now the next thing that we need to discuss is what the Picard group is going to be for these surfaces. And so when you resolve the orbifold singularities, you get a rational curve of self-intersection -3, which is a bisection for the elliptic vibration. The situation with C and D is a little bit more complicated. Okay. Now you could ask me, so like, how do I know this has Cattani dimension 1? Okay. So basically, the answer to this is you go look at some formulas of Cattani. So I'm only going to do a sketch of this. Okay, so in case A, in Cattani's notation, there's one fiber, which is of type 2I0, and there's another one, and there's 24 of these I1 fibers. Okay, now if you haven't seen Cattani's table, maybe we're just going to look at the sketch, and hopefully that tells you enough about what these things mean. So for case A, we're going to start a particular quasi-smooth surface. Okay, so what do I know, by the way? What I know is by this, whatever it was. Okay, I know the Euler characteristic of these things is 24. So happens in case A, okay, the I1 contributes 1 to the other characteristic. I naught contributes nothing, but it's like a double fiber. That's what the 2 means. Okay. So these things always add up to 24. Okay, so how do I get A? Well, I start with this particular equation. And now there's a certain amount of use of the computer to get this equation. So I'm looking at the fiber over, so lambda is 1 over x naught squared. Is x2 over x naught cubed, and w is x3 over x. So this is an affine equation. So maybe I should have said that also. So if you have a weighted projective of the form 1 and a bunch of other stuff, then you can always get an affine chart by dividing out where the variable of degree 1 is non-zero. That won't work if it's P2, 2, 3, 4, or whatever. There you're not going to get affine charts. But if you have a 1, which we do, you can get an affine chart there. So we're just going to write down the equation of the elliptic surface, elliptic surface, but I mean it's a family of elliptic curves in this case. So now we're just going to ask your favorite computer algebra program to take the discriminant of this equation in lambda and z. I'll do that. That will give you the equation without any multiple roots. So that's your 24 I1 fibers. Okay, so now if you, in case A and B, the plane x1 equals 0, because for x0, we still have to do this for x. 0, that cuts the surface in a smooth curve amplitude 3 that passes through a unique singularity, and you can check that this is a smooth curve, which is this reduction of this fiber of type 2I naught. Okay, so that's how you get that's how you get this formula. The k squared equal 1 is something that you can actually then calculate. So, done. So now what do you do with this elliptic pencil structure? Well, what we can do is we can calculate the so-called trivial Picard lattice. So that's the lattice which is spanned by the fibers and one multi-section, in the case there's a section. Okay. Now, there might be more sections. And if there are more sections, the Picard lattice could be bigger. And now there's a type here. This is actually in cases A, C, and D. The behavior of the period map excludes this phenomenon. So what do I mean by that? So oftentimes people say, well, if I have a big Picard group, then that shrinks the size of the image of the period map. Okay, well, you can run that calculation the other way, right? If you can calculate the rank of the derivative of the period map, then that also bounds how many possible Hodge classes you can have on the generic fiber, right? Because if you have, right, it works both ways. If you have a bunch of Hodge classes, that puts a bound on the rank of the derivative and vice versa. So we wrote some code just to calculate the rank of the derivatives of the period maps of these. So in cases A, B, and C, we're confident about what the Picard group is. Okay, so for case A, it's 1 plus minus 1. Case B, if there's no further sections, then it's just this. And in cases C and D, we're confident again. Okay. So I'll just do a simple proof of this. Okay, so in case A, the Picard lattice contains the half of the canonical, so that's the canonical curve, and it has a bisection E, with E times E is -3, coming from the below to singularity. So those gives us classes F and S. And playing around, you see that this gives us the lattice isomorphic to 1 minus 1. And like I said, some calculations with the derivative of the period map will allow us to confirm this. Okay. That's the remark here. Okay, so in case B, what to do? Well, we've talked to a lot of experts in case B. So now I think we're down to another set of techniques. So, of course, the generic algebraic K3 surface has Picard rank 1. But it's really, really hard to find an example of a K3 surface of Picard rank 1. And so one set of techniques for doing that involves reduction mod P. And so there's a student of Ronald Wimnai who's working on case B, so he's trying to write some code to check that there are no extra classes B. So that's where we are with that. Okay. So this trivial Picard lattice means there's nothing else there, so that is a correct answer except B for sure. So our lattices were given up here, and which might be pretty few were the one if you were in what their period maps were. Okay, so I think that is self-explanatory. Questions before I move on? Please don't ask me how this works with reduction mod P, because honestly, I still learn. Okay, questions? Well,
No.
no further. The thing is, well, these period maps. So the period map for a modular just means one coming over the full weighted projective space for the moment. For this combination, structures and emergence for any of the types A and B elliptic surfaces. Okay. So how do you prove that? So first you have to determine the structure to view by means of the Gießen sequence. And now we have to calculate the derivative for the quasi-smooth surface to determine the kernel of the period map, which has dimension 1. Okay? So if you just look at H2 of X prime, the period map has always has a positive dimensional fiber. So we gave another proof of this. This is an old result of I can never pronounce his name, Chirkis, which just says that if you have a family of non-constant family of elliptic surfaces with only one multiple fiber, then the period map always has a one-dimensional fiber. Okay, so we're trying to prove a mixed Torelli. So what do we do? So we want to calculate the derivative of the period map and calculate its kernel, which has dimension 1. And now the next thing that we have to do is what we're going to do, calculate that the direction in which the period map for X prime is constant. And then we're just going to go and see what does that do for the period map to this canonical curve, okay, which is unique. And the answer is, well, you just do a calculation. In that particular direction, the period map for the canonical curve, elliptic curve, is non-constant. So in that way, you just immediately see that the you have a mixed Torelli result. And now I had mentioned some rigidity results at the beginning of the paper. Okay, and so that's corollary, this corollary 5.4 for the surfaces type A and B. The family consisting of the complements of the support economic curve, as soon as the period map has rank greater than or equal to 3, it's rigid. And for C and D, you can do a little bit better, as it only has to be 2. Okay, so, and I guess I went a little bit faster than I went in Ohio. So now I guess I have, maybe this is a good question, so I can talk a little bit about the talk. Is that right? Try and
Something like 8 minutes.
Ciao. I got about 10 minutes left, correct?
Sorry, we can't hear you if you are asking something and I'm not responding, so.
Okay. Okay, so my question was, I think I have about 10 minutes left. Is that correct?
That's correct.
Yes? Okay, so I skipped over this discussion about the global monodromy, but because I wasn't sure if I would have time. But before I discuss the global monodromy, maybe anybody have some questions now.
Greg, maybe I a little bit missed. So what was the main motivation behind this ABC declassification? So at the end, I followed you trying to explain the properties of it in what we know in each ABCD case. But what was the main motivation?
That's a good question. I can go back. So, as I was saying, okay, so a surface of degree 10 in P1125 has geometric genus 2. So the kind of standard compactification techniques where we say, okay, we'll put it in a period domain which has geometric genus 1, and then that's a Shimura variety. I mean, those methods don't work for these particular types of hypersurfaces, right? It's like the first case, right, where you get away from the classical K3, Shimura, et cetera, domains, right? So you would like to compactify them. Okay, so there is a general framework, this KSBA compactification, which allows you to construct compactifications of this moduli space of degree 10 hypersurfaces in P1125. Okay, so that moduli space has dimension 28. Okay, and so I had kind of said 13. So E13 is one of Arnold's list of exceptional unimodal singularities. So what Luca, Patricia, and Zhang and I did was for each of, not for each, but for for the singularities of type E12, E13, E14, W11, sorry, Z11, a second, okay, sorry, E12, E13, E14, then it's Z11, Z12, and Z13, and finally W12 and W13. For each of those singularities, we managed to construct a boundary divisor in this KSBA moduli space. So this boundary divisor has two pieces. So one is this limiting hypersurface. So in the E13 case, it's surfaces which have this equation with this extra condition on what the coefficients is. So if I don't have this 2b plus 5c is greater than or equal to 15, I just get the generic hypersurface of 10. And on this, I get a special sublocus, okay? So these were these E13 surfaces, okay? So basically, what this KSBA compactification does in this case is it adjoins two pieces. So one is a hypersurface whose consists of only these monomials, and the other piece, it turns out, is a K3 surface in a weighted projective space, which essentially corresponds to less than or equal to 15. Okay, I can explain that in details. And so these two pieces are glued together along okay, there's a special point on this. In this case, it's 1, 0, 0, 0, and you perform a weighted blow up and you glue these two pieces together. Okay, so now the question was, what are the birational types of these pieces that go into constructing this KSBA compactification, or these particular boundary divisors in this KSBA compactification? So the answer to that, for the ones of type Z and W, is they're always K3 surface. So you get a K3 surface glued to a K3 surface. That's not a big deal. Now, the next question would be for what happens for these things of type E. And these things of type E are not K3 surfaces. They're these surfaces here. So that's why I was saying that this class of surfaces here naturally produces a surface of degree 14 in P1, 2, 3, 7. Okay, now it happens to also have an A1 singularity there, but of course the usual game is that if you want to look at the ones that have A1 singularities, you should first understand the ones that don't have any singularities. Okay, so so that led us to looking at the property that went into E13. It was clear that these sets of conditions that the amplitude was 1, the two variables were 1 and 2, and we didn't know what the other ones were, but those were an amplitude 1. Those were the key conditions. So we just said, what are all of those possible surfaces? And then after a bit of combinatorics, it's quite remarkable that you only find these 4 cases. Okay, so I mean, I was expecting that one would run this and one would find that, you know, well, you just keep making the degree bigger and bigger, and then there are more and more of these things, but it was a big surprise to me that there were only these 4 cases. And now I don't know if, I don't know how these other 4 cases, if they appear naturally in this KSBA program or not. But that was the original motivation for this, was to understand one particular class of the boundary components in this KSBA compactification. Does that clarify things or no?
Yeah, I think so. Okay, I think it's okay.
Okay. Well, I mean, so that now I have what, 3 or 4 minutes left at most, right? Maybe. Anyway, it's your show.
It is, well, okay, it's finished. The time is.
I can barely hear you. I don't.
The time is finished. But if you want to explain more.
Okay. I mean, I don't know how much I really. I mean, let's just go with, like, yeah. So the monodromy group is as kind of large as it can possibly be, and yeah, maybe I will try and explain the details of that. I mean, I guess there's probably a few minutes between talks to ask me questions privately. And if somebody needs coffee or something, I won't keep coffee.
Yeah.
All right, so sure, I'll stop here.
Okay, thank you.